to the sixth and final part of this mini-series on exponentials and logarithms at the higher maths level. And in this tutorial I'll just be really showing you a practical application of logarithms, which, as I mentioned in the last tutorial, is used tens of thousands of times every day all around the world in science and mathematics. And it's a way of using logarithms to massively simplify the fitting of data and also the interpretation of data. So what I'll do, I think, is just do a bit of maths first to show you how this works, and then we can sort of talk about a couple of examples and why this is so useful. So let's just do a little bit of sort of what might be a little bit dry analysis first, but then you'll see why this is so useful. So what we're going to be talking about here are two different kinds of relationships and how we can simplify their interpretation by using logarithms. So the first kind of relationship would be just a power law. So imagine that we have a function y equals a constant times x to some power, and for the sake of variety I'll just use letter q for that power. And if I were to draw this function depending on the power, I would get some very nonlinear, highly curving function, which actually might be quite hard to interpret. But let's see what happens now if I take the logarithm of both sides of this equation. And it doesn't matter which base I use, so we'll just have an arbitrary base. So I'll take the logarithm of the left-hand side. And remember, I think students are often a little bit wary of manipulating equations. There's only one rule about manipulating equations, which is, well, two rules. The first one is whatever you do to the left-hand side, you have to do to the right-hand side. And I guess the other rule is you can't divide by 0. So you can do anything you like to the left-hand side as long as you do the same thing to the right-hand side. And the only thing you're not allowed to do is you're not allowed to divide by 0, because that makes a nonsense of the equation. So I've taken the logarithm of the left-hand side, therefore I must take the logarithm of the right-hand side, which is looks like quite a complicated thing, but we now get to use our laws of logarithms to great effect. So I have the logarithm of a product of two things, a constant and then this x to a power. So I can use the first of the laws of logarithms to split this into two separate logarithms. So I have logarithm of the first factor plus the logarithm of the second factor. And then I'm sure you'll notice straight away, well, I've got something to a power. I can use the third law of logarithms there and simplify this, which is indeed correct. So I have log to the base little a of the number plus q times log to the base a of x. So this is actually a drastic simplification of that law that we had above, because I had something very nonlinear which, if I drew it graphically, would be quite hard to interpret. So for example, say we were looking at just values of x greater than 0, and say we had x to the power of 4 or x to the power of 5. These would both be very highly rapidly changing functions, which would look actually very similar. Might be quite hard to distinguish them. However, by taking logarithms, what we now have, and this is really such a wonderful thing, is essentially in disguise the equation of a straight line. So let me draw the National 5 equation of a straight line down. Y equals mx plus c. I'm going to write it in a slightly strange way only because of the order in which things are appearing here. But there is, as you'll recognize, the equation of a straight line. I'm using capital letters here just to distinguish between the original y and x. But you see, if I interpret log of y as the thing I want to plot on the y-axis and log of x as the thing I want to plot on the x-axis, I will have a straight line. And the slope of the straight line will be q. So the number that appears as a power in this original law will now be the slope of a straight line when plotting log y against log x. And where that straight line passes through the y-axis, what we call the y-intercept, will tell me the logarithm of that constant sitting outside. So let me maybe just show an example of this then. So let's say we had something like y equals, let's say, 5x to the power of 1/3, okay? Which, if I were to plot that function, would be it would have this kind of shape, it would be some very nonlinear function. But if I just follow this formula here, if I just take the logarithm, I should probably choose a base to be specific here. So let me just choose base 10, just because that's a very common base. And just following that procedure there, I would get log to the base 10 of 5, okay, plus 1/3 log to the base 10 of x. And if I now plot, let's see, if I now plot log to the base 10 of y against log to the base 10 of x, I see that I have a straight line. And in fact, I can even figure out explicitly where it's going to cut through the y-axis. Well, maybe not. I know this number's less than 1. That's all I really... sorry, less than 0, I meant. Because... No, I'm sorry, I'm being a fool here. I know this number is between 0 and 1, because I know that log to the base 10 of 1 is 0, log to the base 10 of 10 is 1, so this number will lie between 0 and 1, and I have a straight line which has a slope of 1/3. So this will be a relatively shallow straight line, and it will cut through the y-axis at a value log to the base 10 of 5. So you might say, well, what's the point of just replotting this? But let's now imagine a different scenario. Say that I'm doing a scientific experiment and collecting data, and say, unknown to me, there is a scientific law that explains that data, which is that the output of my experiment is the input to the power of 1/3. Then, as I'm collecting this data, if I suspect that some power law is underlying that data, if I take my data, and instead of plotting the output data against the input data, if I plot the logarithm of the output data against the logarithm of the input data and plot my data and say I get something which looks relatively like a straight line, I can fit easily a straight line to my data, read off the slope, and in this case I would get a number very close to 1/3, and then I would have a very good evidence that the law underpinning my data is x to the 1/3. So this is how this technique is used in science, is if you have data that when you plot it just against output against input is very nonlinear, it's almost second nature to then immediately plot the logarithm of the data against the logarithm. And if you get something that is very close to a straight line, this immediately tells you that you have essentially something like a power law underlying your data. Now, you might say, yes, but what are the chances that in my experiment there is some power law there? Well, the funny answer is actually highly likely. For reasons that are not really very obvious, many things that we measure in nature actually obey power laws. It's sort of one of the amazing things about the world around us, is that power laws are sort of everywhere. Many of the fundamental equations of physics are, for example, power laws. So just to give you an example, if you were measuring the force between two masses as a function of distance, then you would very likely find that that force goes as 1 over the square of the distance, because that's the law of gravitation. It's also the law of electric fields. So gravitation and electromagnetism satisfy laws that have power laws. Another example would be something just very amusing. So for example, if you were to look at the frequency of occurrence of certain words in a language, then it turns out that the frequency with which words appear in a language obeys a power law. I think that's called Zipf's law. So power laws seem to emerge very naturally in the world around us, and so it's very common to try to do what's called a log-log plot, to see if your data is straightened out by that. If it is, the slope of the data will reveal to you the power. So a very, very cool technique which logarithms enable us to use. Equally useful is the following. If we are collecting data and we have some very, very nonlinear behavior, so more sort of strongly changing than a typical power, we might suspect that there is some exponential going on here. So let's then imagine that we have some kind of exponential behavior. So let me just write it like this. Okay. A priori, I may not know what the base of that exponential is, so I'm just going to write the base as some symbol b there. And again, if I take the logarithms of this equation, what do I find? I find that log of the left-hand side, log of y is log of the right-hand side. I can do the same thing as before. I notice that on the right-hand side, I have a logarithm of product of two factors, and so I can use the first law of logarithms to split that into two pieces. Okay. And then I can use the third law of logarithms to get this power outside of the logarithm. So I will have log to the base little a of capital A plus x now coming outside, log to the base little a of b. You might be wondering, why does Thea use little a and big A when it actually is then quite confusing when I'm speaking these letters, and I apologize for that. I suppose the reason is that little a is a very common symbol that's used for an arbitrary base of a logarithm, and capital A is a very common symbol used for the prefactor of these kinds of laws. So I'm sort of using them because they are actually quite conventional symbols, so sorry for that, making it annoying when I have to keep saying little a and big A. And so here we are, this is what we've reduced this to. And again, you'll see we have the equation of a straight line in disguise. It's a bit different to before. Now I'm going to write it in this way. And I'm going to write little x there to say that actually what we think of as our independent variable x, our input, is actually remains here. So instead of plotting log y against log x, which is what we did in this case, we actually want to plot log y against x directly. This would be called a log linear plot, okay? And the y-intercept would give us information about this constant outside, and the slope actually will give us information about the base of the exponential. Let me, instead of actually doing a direct example of this, let me do a very related example which actually touches and makes contact with something we haven't really talked about very much, which is natural logarithms, so logarithms to the base e. So let's say actually that I was looking at the following example. Let's say I was looking at some kind of exponential decay, and let's say it was something like this. Okay, where I'm using the base of the natural logarithm now, just because we haven't used that very much. Now, it turns out in science that we pretty much use the natural logarithms most of the time, and we use e as the base of exponentials most of the time. So if you suspected that you had some kind of exponential behavior in your data, in using this technique, you would almost certainly take natural logarithms. So I take the natural logarithm of the left-hand side equals the natural logarithm of the right-hand side. And let me do this explicitly. I will have natural logarithm of the right-hand side. I can split that into two pieces. Okay, and then it's a little bit different here, because what I've done is actually I'm using the same base as the base of the exponential here, only because, as I say, in science we typically always think of e as our base of exponentials and logarithms. What's happened then is, instead of having just x as the exponent here, I have x times some number. And so this technique is going to uncover that number for me, okay? So in simplifying, we have log 100, and then we have here minus x divided by 4 of log to the base e. But natural log to the base e is just unity, because this is log to the base e of e, which is just 1. And so how would this appear then if we plotted natural logarithm of y against x? We would now have a straight line with a negative slope, which is quite, again in this case, quite shallow, and it passes through the y-axis at the value natural log of 100. Okay, so it looks something like this. And this value here is natural log of 100, and the slope is negative 1/4. I should just indicate that here. So this is slope of 1/3. This is slope of negative 1/4. And again, so if I was, for example, looking at something like radioactive decay, which is the classic example of exponential decay, but I could also be looking at, some ecological problem, for example, where I have a species which is in decline, and I could be measuring population numbers each year, and if they're really in terrible decline, that may follow an exponential law. And if I suspected an exponential was going on behind the scenes, I would do what's called a log linear plot. I would just take a logarithm of the output data and plot that directly against x. And if there was an exponential there, again, my data points would indicate that there is some kind of straight line behavior. Okay, and the slope of this line then gives me information about what's multiplying x up in the exponential, which would essentially tell us about the rate of decline. In the radioactivity example, that's often related to what's called the half-life, which I think we briefly mentioned when we talked about exponentials. So I'll stop here with this particular topic. This can appear at first a little bit sort of abstract, but it's an incredibly useful tool, and it's used by scientists and mathematicians, as I say, countless times a day in simplifying data analysis. Just to recap very briefly, if I suspect I have a power law underlying my data, I would perform a log-log plot, and this would then reduce this to the equation of a straight line on a log-log scale, as I showed with this example. If I suspected I have an exponential sort of hiding in my data, I would do a log linear plot, take the logarithm of both sides, and the exponential behavior means then that x appears explicitly, and a log linear plot will again reveal a straight line. So, the wonderful power that logarithms have provided us to do calculations and to analyze data, even though they seem a little bit abstract at first, as the inverse of exponential functions. So I hope that's been helpful. That's the end of this mini-series on exponentials and logarithms. We will see them again soon, though, because I'm going to just record an optional tutorial as part of the calculus series showing you about the derivatives of the exponential function. It's something that's just too good to miss. It's not required in the higher syllabus, but it's really something that you would understand very straightforwardly, and it would give you some great insight as to why we use the number e as the base of exponentials and logarithms, because without seeing the calculus of this, you would still be rather perplexed why this number e is so special. Right, so hope that's been helpful, and I look forward to seeing you next time.